In the last lecture, we have introduced RSA crypto system, which is based on factoring large integers, hardness of factoring large integers. Also, we have introduced LGAML encryption scheme, and why LGAML is preferable over RSA. We also have mentioned that RSA encryption scheme is deterministic, whereas LGAML encryption algorithm is probabilistic. And another difference between these two crypto systems is that discrete LGAML encryption scheme is based on the hardness of discrete log problem. Now, in this lecture, we will go through certain more number theory. We will discuss the properties of Euler's phi function. We have used those properties several times. So we are going to give a proof of those properties, and while doing that, we will also give a proof of Fermat's-Little theorem, a very simple proof, and it is Euler's theorem. Okay, so those things we are going to cover in this lecture. This first result, this was asked as an exercise. Anyway, let me go through this. So it says that given two integers a and b, a is congruent to b modulo m if and only if a and b leave the same remainder when divided by m. So a is congruent to b modulo m. How we define? This means m divides a minus b. Okay, so this congruence holds means a and b leave the same remainder when divided by m, and the converse is also true. If a and b leave the same remainder when divided by m, then you can prove a congruent to b modulo m. Okay, so using division algorithm, you can easily prove this. So a congruent to b modulo m, and suppose r be the remainder when a is divided by m. Okay, so that means what? That means by division algorithm, a equal to some q into m plus r. When a is divided by m, remainder is r, so a is qm plus r, where r is the remainder lying between this range, 0 less or equal to or less than m. Okay. Now, since a is congruent to b modulo m, this is given. A minus b is divisible by m. That means a minus b is some multiple of m. K is some integer km. This is equal to km. So my claim is that if a leaves the remainder r when divided by m, we have to show b also leaves the same remainder when divided by m. You can prove this very easily. So from here, I get b equal to a minus km. Now by division algorithm, a is this, qm plus r, just substitute, and you can see that b can be written as some integer multiple of m plus r. Okay, very simple proof. So b also can be written as this, r is in this range. When b is divided by m, it is some constant multiple of m plus r. It shows that b leaves the same remainder r. Okay. Converse is also very trivial. If r is the remainder, when a and b are divided by m. So from here, a is some q1 m plus r, and b is also q2 m plus r, where q1, q2 are integers. And this r is, by division algorithm, this r is in this range. Okay, then you can see that a minus b is q1 minus q2 m. So integer multiple of m. So m divides a minus b, that means a is congruent to b modulo m. So whatever exercises are given in the number theory lecture regarding this congruence, you can prove all those if you just remember the definition of congruence. Congruence, this definition is a congruent to b modulo m means m divides a minus b. Okay. Now the next result, this is very important for us. We are using this in several places. Okay, AC is if AC is congruent to BC modulo M, and the C and M are their GCD is D. If AC is congruent to BC modulo M and GCD of CM equal to D, then A is congruent to B modulo M over D. Okay, so this theorem we have used in several places. So, for example, if suppose GCD of CM equal to C, suppose that means C divides M. If C divides M, then in that case GCD of CM equal to C. Okay, C divides M. So AC congruent to B, C modulo M, and C divides M. So in that case GCD of CM is C. GCD of CM is C. Then by this theorem, A is congruent to B. A is congruent to B modulo M over C. Means throughout this equation, I divide this by C, also this by C. That already we have used while finding the solution of linear congruence modulo an integer. We already have used this result, that the AC congruent to BC modulo M, and so this result we have used. Okay, in this case, and more from this, another corollary I can derive. Suppose GCD is 1, GCD of CM is 1. GCD of CM is 1. If GCD of CM is 1, if GCD of CM is 1, then this C I can cancel out from both sides, and GCD is 1 means this essentially this congruence gives me A congruent to B modulo M. So this cancellation law holds provided C and M are co-prime. This result also we will use. So the proof from this result, these two corollaries follows. These two corollaries follows. Okay, so AC congruent to BC modulo M, and M and C, these are co-prime. Then in that case C you can cancel out. And if AC congruent to BC modulo M and C divides M, when C is sitting inside M as a factor. So in that case, this relation implies A is congruent to B modulo M over C. Okay, both these follows from this theorem. Proof is very simple. Okay, means let me skip the proof. You can go through this proof. Very simple proof. Means you have to utilize this result. Given this and this, you have to show. Okay, AC is you just go through the proof. It is not that difficult. The next one is this is also very useful result for modular operations. If A is congruent to B modulo M, then you can raise A to the power n and B to the power n. Okay, then also it is for any positive integer. So A congruent to B modulo n means A to the power n is also congruent to B to the power n modulo n for all positive integer n. Okay, so both sides, any number, any exponent, same exponent you can raise. They are also congruent. Okay, so the proof by induction, the proof is done. Now we are interested in this definition. So a set of m integers r1, r2, rm. So this set of m integers is said to be a complete set of residues modulo m, or a complete residue system modulo m. This is a complete set of complete residue system. We say this is a complete residue system modulo m if no two elements in this set are congruent modulo m. No two elements in this set are congruent modulo m. So this is called This is called a complete residue system modulo M. So for example, if you consider 0, 1, 2, M minus 1, this set is an example of a complete set of residue modulo M. If you pick any two pair from this set, okay, so they are not congruent modulo M. This is an example of complete set of residue modulo M. From here, this definition actually suggests that R1, R2, Rm, this is essentially congruent to 0, 1 to m minus 1 modulo m, not necessarily in the same order. So this set, this R1, R2, Rm and this 0, 1 to m minus 1, these are essentially same, maybe in some other order. So we are considering complete residue systems modulo m. So modulo m means the integers are in between 1 to m minus 1. And this is this set of integers complete residue system modulo m if no two elements are congruent modulo m. This is the definition. Okay. So if you have a complete residue system modulo m and C, you pick any integer C, then C plus R1, C plus R2, C plus Rm is also a complete residue system modulo M. This is a complete residue system modulo M. C is any integer. So so this is a complete set of residue modulo M, and if you add any constant to all the elements, that set is also the resulting set is also a complete residue system modulo M. So if you reduce it modulo M, it will give you a set same as this but in some other order. So only thing we have to show that given this is a complete set of complete residue system modulo M, you have to show this is also a complete residue system modulo M. That means none of these elements pairwise, any two elements you pick from this set, they are not congruent modulo M. So we need to show this. If I not equal to j, then C plus Ri not congruent to C plus Rj modulo M. Okay, it follows from the fact that Ri, Rj are not congruent modulo M because this is a given complete set of residues modulo M. Okay, since Ri, Rj are from complete set of residues modulo M, Ri not equal to Rj. So M is not a divisor of Ri minus Rj. So if you take C plus Ri minus C plus Rj, this is Ri minus Rj. So Ri minus Rj not divisible by M means C minus Ri minus C minus Rj is not divisible by M. That means C minus Ri not equal to C minus Rj modulo M. Okay, so given a complete set of residues modulo M, if you shift every element by the same amount, adding, okay, shifting each element by the same C amount, then it is also a complete residue system modulo M. What about product? Complete set of residues modulo M, and I'm now considering, instead of addition, I'm considering CR1, scalar multiplication, CR2, CRm. In that case, it is also a complete set of residues modulo M, provided there is some constant. There is some, let me, this here. So if you consider the product, then this AR1, AR2, ARM is also a complete set of residue modulo M, provided A and M are co-prime. Okay, this condition is needed. This also you can prove. And while proving that, you have to utilize the corollaries that I mentioned earlier. Okay, so Ri not equal to Rj modulo M. From that, you have to show ARI not equal to ARJ modulo M. You can utilize the corollaries of the theorem that I have mentioned earlier. So from this I get this corollary from this multiplication and addition of this complete residue system. Okay, so I get this. So I'm taking C plus A, C plus 2A, C plus M minus 1A. So I'm considering the set means I'm considering the set 0, A, twice A, M minus 1A. So my complete residue system is 0, 1, 2, M minus 1. I take the constant multiple, just multiple of scalar multiple of by A of every element of 0, 1 to M minus 1. So A into 0, that means 0, first element is 0, then A, twice A, M minus 1A. And then shift by C plus 0, C plus A, C plus twice A, C plus M minus 1A. So this is also a complete set of residues modulo M. Provided condition here is A, when you take a scalar multiple, that A and M should be co-prime. And C is any constant. C is a constant. Okay, so it follows from the previous two theorems. Okay, this theorem you can prove the shifting by C, the addition that we have discussed. So this actually plays, this result actually plays an important role in proving the properties of Euler's phi function. Means specifically to prove that Euler's phi function phi is multiplicative. We are going to utilize this result. Okay. Now I have a proof of Farmer's little theorem here. Since I have the proof, let me go through this. This is very simple proof. So so many times I have mentioned this. If P is prime and A is co-prime to P, that means P does not divide A. Okay, so in that case, A to the power P minus 1 is congruent to 1 modulo P. Okay, so if P is prime and P is not a divisor of A, that means GCD of AP equal to 1. In that case, A to the power P minus 1 is congruent to 1 modulo P. Okay, so to prove that, what we will do, we consider the integers A, twice A, thrice A, P minus 1A. So first claim is none of these elements are divisible by P. It actually comes from Euclid's lemma. In Euclid's lemma, we have discussed earlier in Euclid's lemma that if P divides AB, P is prime, suppose P is prime, P divides AB, then either P divides A or P divides B. So here, if P divides any element, that means P either divide A or P divide this element TA. Suppose some element, I take TA element from this set, T times A. So either P divides A or P divides T. But P does not divide A, it is given, so P must divide T. But T ranges from 0 to P minus 1. So T cannot divide, P cannot divide T also, because T is in the range, T is less than P. It is actually, it belongs to 0, 1, 1, 2, 3 up to P minus 1. So first note is that none of these elements are divisible by P. It actually follows from Euclid's lemma. This is Euclid's lemma. Okay. Now next claim is no two elements of this set are congruent modulo P. No two set of elements, no two set of elements in this set, no two elements here is congruent to P. Means if you take two elements, suppose RA and SA, two elements you take, RA and SA, they are suppose congruent modulo P, then what happens? If RA and SA from this set are congruent modulo P, then mind that these R and S are ranges from 0 to P minus 1. And suppose R is less than S. So we are getting this R 1 less or equal to 1 less or equal to R. Suppose R is less than S. Okay, so two elements I am picking from here, RS, RA and SA. So suppose R is less than S, and this is less or equal to P minus 1. So they are in the range from 1 to up to P minus 1, R and S, and suppose R is less than S. Okay, so so you can say that A is co-prime to P. Then I can utilize the corollary. And I can cancel out this A from both sides. So RA congruent to SA modulo P. This implies R is congruent to S modulo P. This is essentially contradiction because R and S are within this range. Both are less than P minus 1 and are less than S. So this gives a contradiction. So if two elements from this set are congruent modulo P, then we are getting a contradiction. R is congruent to S modulo P. It cannot be true because they are in this range. R and S are in this range. So first claim we have shown that none of these elements divisible by P, and second we have shown that none of the pair of elements, if you pick pair of elements, they are not congruent modulo P. So essentially we have shown that if you consider this set A, twice A, thrice A, P minus 1A, this actually forms a complete set of residues modulo. It's not complete set of residues modulo P. Because 0 is not included. Okay, complete set of residues modulo P means 0 is also included. 0 is also included. No, it's not complete residue system, but what you can we can say that the integers A, twice A, thrice A, P minus 1A, these are congruent to 1, 2, 3, P minus 1 modulo P. Modulo P. Okay, so none of these elements are divisible by P, and if you pick any two elements, they are not congruent modulo P. So if you consider A, twice A, thrice A, P minus 1A and reduce all of them modulo P, then you will essentially get this set 1, 2, 3 up to P minus 1 in some order. Okay, so if you multiply this, so this multiplication of all these elements is congruent to multiplication of all these elements modulo P. Okay, so from here A to the power, how many elements are there? A's are there? A to the power P minus 1, factorial P minus 1, factorial P minus 1 modulo P. Now factorial P minus 1 does not have P as a factor. Okay, so P and factorial P minus 1, they are co-prime. Their GCD is 1. So again we can apply that corollary and cancel this out. Okay, cancel this out. So this actually gives A to the power P minus 1 is congruent to 1 modulo. This is your Farmer's little theorem. Okay. Okay, so the result may be stated in a more general form. Means we have written this A to the power P minus 1 congruent to 1 modulo P when A and P are co-prime. That means P does not divide A. Okay, so if P is a prime, A is any integer. For any integer, it may have P as a factor and may not have P as a factor. So for any integer, we can write in this way: A to the power P is congruent to A modulo P. Okay, so in case P is not a divisor of A, then Farmer's little theorem gives this result, and for both sides you can multiply simply by A, you get this result. And in case P divides A, then A to the power P actually is congruent to 0 modulo P. When you divide by P, it is congruent to 0 modulo P, and right hand side is also A modulo P is also 0. So this case also, in this case also, this relation holds. Okay. And another thing is, this is your Farmer's little theorem. P is prime number means P odd prime. Actually, P is odd prime, and a to the power P minus 1 is even number. Okay, except when P equal to 2. So when P is odd prime, P minus 1 is an even number. So you can factor this. A to the power P minus 1 is 0 modulo P. So this is a to the power P minus 1 by 2 plus 1. A to the power P minus 1 by 2 minus 1 is 0 modulo P. So this means this product is 0 modulo P means P divides either this one or this one. Okay, so a to the power P minus 1 becomes some constant multiple of P plus 1 or some constant multiple of P minus 1. K is some, this K is some positive integer, some integer. Okay, so using this we can prove that cube of any integer is always of this form, 7k plus 1, like that. 7k plus 7k, 7k plus 1 or 7k minus 1. Okay, it means if P is 7, then it is of the form 7k plus minus 1. Okay. Okay. Means essentially it says that any integer, cube of any integer, when you divide it, divide the cube of any integer by 7, then either remainder is 0 or remainder is 1 or remainder is minus 1. So this essentially gives you the result that a to the power P minus 1 by 2, a to the power P minus 1 by 2, this is congruent to plus minus 1 modulo P. Plus minus 1 modulo P. When you take modulo P, right hand side this value cancels out. So anyway, now, so same way Euler's theorem also you can prove. The proof is almost same. The proof is almost same. So you have to start here. We have started when we prove it. We have started with this. Actually, this is a residue system. Means 0 is excluded, excluding 0. Okay, this is actually a residue system. Modulo P. So here also we start with integers. So a1, a2, a phi n. These are integers less than n and co-prime to n, which are less than n and co-prime to n. So I have to show a to the power phi n is congruent to 1 modulo n when a and n are co-prime. Okay, so we take integers which are less than n and co-prime to n. So these are there are phi n many such integers. That is the definition of phi n. That number of this is the number of integers that are less than n and co-prime to n. So those integers I list those integers, denote those integers by a1, a2, a phi n. So those integers are all less than n and they are co-prime to n. Okay, you start with that. Instead of starting with 1 to p minus 1, like in case of Fermat's little theorem, we start with this and take these products a1, a2, a phi minus 1, phi n. Then you prove first lemma that none of these are divisible by n. And the second lemma, if you take pairs, any two pairs, they are not congruent, means AR and AS, they are not congruent modulo n. Okay, so same way you can prove. Okay, I will just go through this. Okay, so these two claims you prove, and then you can say that this product essentially gives you this product. From here, a to the power phi n, you get a to phi n many is a to the power phi n is congruent to 1 modulo n. It is cancellation holds because n is co-prime to each of a2, a3, a phi n. That means GCT of n and a1, a2, a phi n is 1. This also, there also we apply Euclid's lemma, general form. Okay. Okay, you go through this same proof. Now we can prove Euler's, the properties of Euler's phi function. First property was if p is prime and k is any positive integer, p is prime and k is any positive integer, then phi p to the power k is p to the power k into 1 minus 1 by p. Okay, so this we can prove utilizing the definition of phi function. So what is phi p to the power k? The phi p to the power k is the set of positive integers which are less than equal to p to the power k and co-prime to p to the power k. So we have to show that number is this. Now list the positive integers which are less or equal to p to the power k and not co-prime to p to the power k. So not co-prime to p to the power k means these are actually multiples that has p as a factor. So p, twice p, thrice p, p to the power k minus 1 p. So these many integers are less or equal to p to the power k which are not co-prime to p to the power k. So these are the integers. How many integers are there? 1, 2, 3 up to p to the power k minus 1. So p to the power k minus 1 integers are there which are less or equal to p to the power k and not co-prime to p to the power k. So number of positive integers less than p to the power k and co-prime to p to the power k will be, so total how many integers are there? Positive integers are there less or equal to p to the power k, that is p to the power k. And how many are not co-prime? P to the power k minus 1 many. So how many are co-prime to p to the power k? P to the power k minus p to the power k minus 1. So total number of positive integers less or equal to p to the power k is p to the power k, and positive integers less or equal to p to the power k and not co-prime to p to the power k are these elements, explicitly these elements. So there are p to the power k minus 1 non-co-prime elements which are non-co-prime to p to the power k. So if you subtract, you get the number of positive integers less or equal to p to the power k and co-prime to p to the power k. So this value is essentially same as this value. Okay, so this proof is easy. Now to prove the second result, and mainly this, when m and n are co-prime, then phi mn is phi m into phi n. That means this Euler's phi function is multiplicative function. Phi of mn equal to phi m into phi n provided m and n are co-prime. This result, to prove this result, we have to prove certain lemmas. We are going to utilize certain lemmas. The third one, we will discuss that. The third one is the more general formula that if n is having the prime factorization p1 to the power a1, p2 to the power a2, pr to the power ar, where p1, p2, pr are co-prime to one another, then phi n is this n times 1 minus 1 by p1, 1 minus 1 by p2, 1 minus 1 by pr. Okay, so using the previous two results, means this one we already know. Phi p to the power k is p to the power k times 1 minus 1 by p. So that result we have proved, and also suppose the multiplicative property holds. Suppose we are going to prove this. So for the time being, let us suppose we have already proved this thing. Phi mn equal to phi m into phi n whenever m and n are co-prime. Utilizing that, I can get this proof. Or you can utilize the induction also. So essentially, phi p1 to the power a1, if you have only one prime power, in the factorization one prime power, this is simply p1 to the power a1, 1 minus 1 by p1. Phi p2 to the power a2 is this, phi pr to the power ar is this. Now, since p1, p2, pr are co-prime, p1, p2, pr are relatively prime, mutually relatively prime. So, p1 to the power a1 and p2 to the power a2 are also co-prime. Okay, p1, p2 are co-prime means p1 to the power a1, p2 to the power a2 are also co-prime. Okay, so if I apply the multiplicative property, phi of p1 to the power a1, p2 to the power a2 will be equal to phi of p1 to the power a, phi of p2 to the power a2. If you substitute these values here, you get this. Again, p3 to the power a3 is co-prime to this product, because p1, p2, p3 all are co-prime. So p3 to the power a3 is co-prime to this product. So I can get from here phi of p1 to the power a1, p2 to the power a2, p3 to the power a3 by multiplicative property. This will be equal to phi of first 2 into phi of this. Again, I can plug this value here. So that way we can get the result. Okay, so you can utilize induction also to prove this. Now the main part is to prove m and n are whenever this multiplicative property of Euler's phi function. So for that, I need to go through. I need to use certain lemmas. First lemma is this one. A is co-prime to mn if and only if A is co-prime to m and A is co-prime to n. A is co-prime to mn if and only if A is co-prime to m and A is co-prime to n. That means GCD of A mn equal to 1 if and only GCD of am equal to 1 and GCD of an equal to 1. Okay, so I'm not going to discuss this proof. Just go through this. Okay, very simple proof. Without seeing this, try to do it by yourselves. Okay, so given GCD of AMN equal to 1, prove that GCD of AM is 1, also GCD of AN is 1. And converse also. So try to do it by yourselves. Next lemma is if R is the residue of a modulo n and R is co-prime to n, then A is co-prime to n. Okay, if R is the residue of A modulo n, that means A is some Qn plus R, and R is co-prime to n, that means GCD of n are equal to 1, then A is co-prime to n. A is co-prime to n. Earlier, we have proved this result. Okay, GCD of n is GCD of Qn plus R, comma n. A is Qn plus R. And while proving the Euclidean algorithm, we have seen that this GCD is same as GCD of Rn. GCD of Rn is 1. So GCD of R, if R is co-prime to n, then A is also co-prime to n, because GCD of AR is same as GCD of AN is same as GCD of Rn. Okay, GCD of Qn plus Rn is same as GCD of Rn. GCD of Rn. This lemma says if C is any integer and A is co-prime to n, then if you consider this set C C plus A, C plus twice A, C plus n minus 1A. This is a complete residue system modulo n, right? So how many elements, how many integers are there in the set which are co-prime to n? How many integers are there which are co-prime to n? This is phi n. Okay, so if C is an integer, A is co-prime to n. See, I am taking a scalar multiple by A of the set 0, 1 to n minus 1, and shifting by C plus 0, C plus A, C plus n minus 1A. So how many elements in this set are co-prime to n? That is the number phi n. Okay, so this theorem actually follows from this. No two integers in this set are congruent modulo n, because if you take C plus SA equal to C plus TA modulo n, where S less than T and they lies between 0 to T n minus 1, they lies between 0 to n minus 1, this range. C plus SA, some elements C plus SA and C plus T I have taken. So S and T both are in the range 0, 1 to n minus 1. And suppose S is less than T. So if this holds, then C I can subtract, and this A I can cancel because A and N are co-prime. So we are getting, if this holds, then this holds. This is a contradiction because they are in this range. So none of these, no two elements in this set are congruent modulo n. So if you reduce this system modulo n, you actually will get this set 0, 1 to n minus 1. So this is actually complete set, a complete residue modulo n, and this is when you reduce all these elements modulo n, you get this set in some order, not necessarily in the same order, in some order. And how many elements are there in this set which are co-prime to n? This is essentially number of elements less than n and co-prime to n, that is phi n. Phi n many integers in this set are co-prime to n. So this is also how many elements will be there co-prime to n, same element, because this system both are complete residue systems modulo n. So number of elements co-prime to n in this set, number of elements co-prime to n are phi n. So in this set also number of elements co-prime to n will be phi n. Follows from this fact. So now I am in a position to prove this. So if since phi 1 equal to 1, so when m and n are equal to 1, then it trivially follows. M or n equal to 1, it trivially follows. Now suppose m is greater than 1, n is also greater than 1. So what I will do, so here how many elements I have to, this left hand side actually counts number of elements less than mn and co-prime to mn. So all the integers from 1 to mn I write in this array. Okay, 1, 2, 3, m, then m plus 1, m plus 2, twice m plus 1, twice m plus 2, thrice m, n minus 1, m plus 1, n minus 1, m plus 2, n. This way I write. Okay, so this is 1, 2, 3, some r, then m plus 1, m plus 2. So this we write all the elements in mn into this rectangular array. Okay, now in a first row, 1, 2, 3 are m. How many elements are there which are less than m and co-prime to m? So there are how many elements in this which are co-prime to m? Pi m many elements. Okay, so if you use lemma 2, so this 1, 2, 3 up to lemma 2 means okay, so lemma 2 lemma 2 how many elements are there which are co-prime to M? High many elements. And suppose this is this column, how many elements are there which are co-prime to so this is suppose co-prime to N. Now how many elements are there which are co-prime to N? So this is actually if you apply lemma 3, then this is R M twice M n minus 1 M. So how many elements are there which are co-prime to N? That is phi n. This is by lemma 3. Lemma 3, you see that this modulo n. So this is a this set C plus A, C plus twice A, C plus n minus 1. This is the complete residue system modulo n. And there are phi n many elements which are co-prime to n. So in this column, there are this is a complete residue system modulo n. And how many elements are there which are co-prime to n? Phi n many elements are there which are co-prime to n. Now this element is co-prime to m. This element is co-prime to m. This element co-prime to n. How many such columns are there which is co-prime to m? 1, 2, 3 up to m. Okay. So in the first row, number of elements less than m and co-prime to m. This is phi m many elements. In the second row, if you take modulo, if you take how many elements in the second row which are co-prime to m? So this is essentially m plus 1, m plus 2, m plus 3, m plus r twice m. If you take modulo m, this is essentially same as the first row. Every element, every row is if you take modulo m, it is essentially the first row. Modulo m means essentially first row. And in the first row, how many elements are there which are co-prime to m? Phi m many. Suppose this r is co-prime to m, then all the elements here are co-prime to m, because this element is modulo m. If you take all these elements, give you same r modulo m. So if r is co-prime to m, then this whole column, all the elements are co-prime to m. Okay, so we get this is essentially a complete residue system modulo m, and they will give the same remainder r when take modulo m. When take modulo m. So phi n. So out of them, phi n integers are co-prime to n. Out of them, phi n integers are co-prime to n. Okay, so this is the idea. You have to apply lemma to first row, second row, third row. All are in modulo m. If you take, all rows are essentially same as the first row. And in the first row, how many elements are there co-prime to m? That is phi m. So if this is co-prime to m, then these are all co-prime to m. And all these elements are co-prime to phi m. Out of them, the elements which are co-prime to n, that is only phi n many elements. Out of them, only phi n many elements are co-prime to n. So this is the idea why we are getting phi m equal to phi n into phi n. Okay. And also we are using lemma 1, which states that an integer is co-prime to mn if and only if it is co-prime to both m and n. Okay, so all these elements we count, all these elements up to mn we write in this way, and we are essentially counting how many elements out of these mn elements are co-prime to both m and n. If both are co-prime, if an element is co-prime to both m and n, then it counts here also. Okay, so that is essentially counted here. Okay, so number of integers among these that are co-prime to mn is phi mn. Now by lemma 1, these integers are both co-prime to m and n by lemma 1. Now number of integers in the first row that are co-prime to m, 1 to m, 1, 2, 3 are m. There are phi m many integers that are co-prime to. In the first row, there are phi m many integers which are co-prime to m. Okay, co-prime to m. So 1 to up to m, less than number of integers less than m, co-prime to m is phi m. And if you apply lemma 2, each integer in the column r lies between 1 to m, is co-prime to m if r is co-prime to m. Each integer r in a column r, it is co-prime to each integer in the column r is co-prime to m if r is co-prime to m. One element is co-prime to m means each element is co-prime to r is co-prime to m. Each integer in the column r is co-prime to n if r is co-prime to m. All these elements co-prime to m if r is co-prime to m. Because essentially when you take this is essentially a complete residue system modulo n. So when you take modulo m, this set actually gives you same remainder r. So all of them are co-prime to m, provided r is co-prime to m, because they leave the same remainder after dividing by n. Okay. So there are phi m columns of integers prime to co-prime to m. Again apply lemma 3. Each column is the arrangement contains phi n integers prime to n. Okay. So from here it follows. So you just go through this reasoning. Thing is row wise you apply lemma 2. So phi m many integers co-prime to m. And a column is co-prime to this r is co-prime to n, then this column every element here co-prime to n, because every element when reduced modulo m, it essentially gives you the same remainder r. So r co-prime to m means every element here co-prime to m. Now out of them, how many elements are co-prime to n? That is essentially phi m many. So phi m many columns are co-prime to m. Out of them, phi m many columns, in each of these phi m many columns, suppose this is one of the phi m many columns, out of them all are co-prime to m, as well as phi n many are co-prime to n. So there are total phi m into phi n many elements in this array which are co-prime to both n and n, and by lemma 1 they are counted here also. So this is it. Okay, this completes the proof. This completes the proof. Okay, let us stop here. The one thing I want to mention here, so RSA based public key crypto system we have introduced. Discrete log based crypto system also we have introduced. Another crypto system, public key crypto system, knapsack problem, Markley-Hellman knapsack crypto system, and that actually uses the subset sum problem or 0-1 knapsack problem. Based on that, crypto system is designed called Markle-Hellman crypto system that we will discuss in the next class. Because subset sum problem, general subset sum problem or knapsack problem, 0-1 knapsack problem is NP hard problem. Okay, based on that, it derives a security. We are going to discuss that crypto system in the next class.